Hello everyone, this is Philip Myers from PEMY Consulting. We have an update on the COVID-19 virus as of 4/22/20. The data comes from Johns Hopkins University, and we think it's one of the better data sets out there. We are an engineering company and we look at the data from the perspective of plots and graphs. At the same time, I want to disclaim the following. I'm not a doctor, I'm not an epidemiologist, and I'm not making predictions. I'm just showing you the benefit of seeing the graphic plot of the total number of COVID cases in the U.S. In addition, after we go through the plots, we have an animation that shows the growth of COVID-19 in every county in the United States from the first case until April 22nd. As a reminder, you've no doubt heard that the COVID-19 is growing exponentially, but it actually does so only in the beginning. You can see that the logistic curve is a more realistic growth model. It says that there is a limit shown by the dotted line beyond which growth does not occur. This is because of a shortage of food for animals, or in the case of COVID-19, a shortage of susceptible people, maybe perhaps due to herd immunity. In any case, the logistic distribution seems to be the one that fits the data best at the current time. Another characteristic of the logistic growth is that it starts slowly, as you can see by the green slots on the left and on the right, and it finishes up very slowly. The most rapid growth occurs at half of the carrying capacity, or the maximum number of people that would be infected by the disease. This is a linear plot of COVID cases by date. On the y-axis, each line is 100,000 people. You can see that as of today, we're over 800,000 cases. The red line shows a logistic curve. The fit's not so great at the knee of the curve at about late March, but it is much better near the end. It looks like the logistic curve is underestimating that last point, but that's just noise in the data, so we'll see how this comes out ultimately. This is the same plot as previously shown, except on the y-axis we have a log scale. The top grid line is 1 million COVID-19 cases. In the beginning, the fit's not very good, and I suspect that's because the underreporting of actual cases, so it doesn't follow the black line, which is the logistic curve, and at this phase it would be exponential as well. But once we get into mid to late March, the logistic fit is quite good. This may be the most informative plot of all. It's a log-log plot. That is, the number of cases on the x-axis is on a log scale. It goes from, you can see, 1e plus 0.02, that's 100, up to the right-hand side, which is 1 million. On the vertical scale, we have log of the relative growth. The relative growth is the amount by which the new cases as a percentage of the current cases changes. On this plot, a horizontal line represents exponential growth. The dots are the actual data, and the black line is the best fit logistic regression. You can see that the horizontal part pretty well shows that we've had an exponential growth, but at the knee of the curve, it's tapering off very fast, so the maximum growth rate has decreased. Here is a map of the United States. It starts with the first reported case in January 20th in Washington. You can see that each point is a small red dot. 1,000 cases is shown at this size, 10,000 and 50,000. In this time-lapse video of the spread of the disease, you can see that exponential growth is occurring, but it's very difficult to see the taper off that we were talking about. Up here, watch the days. They will be counting off starting from January 2nd and end on April 21.